In this next video, we're going to relate work done on an object and its resulting kinetic energy. Now here we have an example. We have a mass equal to 2 kilograms, a force of 10 newtons pushing to the right on a frictionless surface for a distance of 100 meters. So let's figure out how much work we have done on the object and what its resulting kinetic energy will be. Since there is no friction, we don't expect any energy loss due to friction. That would then be assumed that all of the work is then converted into kinetic energy, none of it in potential energy because no height is gained. So starting with the equation, work is equal to force times distance, and of course these are vector quantities, so we use the dot product. And in this case, since the direction of the force and the direction of the displacement are the same, the angle between them is 0, the cosine of 0 is 1, and so we can say that this is simply equal to force times distance, which is 10 newtons, times 100 meters, which is 1,000 newton meters, which is 1,000 joules. And we can then assume that all of this work is then converted in kinetic energy, and we then assume that the block will have 1,000 joules of kinetic energy when it reaches the end of the 100-meter trip. All right, another thing we can do, we're going to show in just a moment that that's indeed the case. Another thing we can do is figure out how fast the object will be moving when it reaches that distance. Since we don't know how long it's going to take, we can use the equation that says v squared is equal to v initial squared plus 2 times acceleration times x. So the acceleration, of course, can be found by knowing the force and the mass. Using Newton's second law, we can say acceleration is equal to the ratio of the force divided by the mass, which is equal to 10 newtons divided by 2 kilograms, which of course is going to be 5 meters per second squared. So we also know the acceleration. The initial velocity would be 0, so this would be plus 2 times 5 meters per second squared times the distance of 100 meters. And that will be equal to v squared. If we take the square root of both sides, we get that. So that means the end velocity will be 2 times 10, that's 10, that's 1,000. That would be about 31 point something, I suppose. Let's see, 1,000, take the square root. 31.6 meters per second. So the fact that it's moving at a fairly high velocity after 100 meters, it will have a substantial amount of kinetic energy, which we assume to be 1,000 joules. But let's figure out a way to calculate that straightforward with the right equation. The concept here would be to say, let's figure out that if we move the block a small amount, dw, a small amount of work is done. So let's say that we move the block a small distance dx, using the force of 10 newtons, pushing it to the right. So we'll do a small amount of work, and that small amount of work will be equal to the force applied to the block times the small amount of distance that we achieved, dx. And if we then use Newton's second law and write F equals ma and replace the F by ma right there, we can then write that dw is equal to m times a times dx. And then if we replace a, acceleration, by what a is equal to in terms of velocity and time, we can then say that dw is equal to the mass times dv dt, that's the definition of acceleration, times dx. Then if we move the dt over here, we don't have to do that, but just to make it more visible, we can write dw is equal to mass times dv times dx dt. And of course, the definition of dx dt is that that's equal to the velocity, which means that dw is equal to m times v times dv. I just moved the dx dt, which is v, over in between m and dv. And then I can go ahead and integrate both sides. So integrate the left side, integrate the right side. Of course, m is a constant, so we get w is equal to m. The integral of v dv is v squared over 2. In other words, the work done to get the object from there to its final position, we can then say to its final velocity is equal to 1/2 mv squared. So that would be the work required to move that block from here to there. In that case, it will have gained a certain amount of velocity, and that way that work is then turned into kinetic energy. So by definition, we can say that this work will then become the kinetic energy of the object, which is equal to 1/2 1/2 mv squared. And now we have the definition of how to calculate kinetic energy of an object. If we now plug in the mass and we plug in the velocity that we know that it obtained, we hopefully should end up with 1,000 joules. So let's find out. Kinetic energy is equal to 1/2 times the mass of 2 kilograms times the velocity of 31.6 meters per second squared. And if we remember right, if we square the number that we obtained before, we should get 1,000 times 1/2 times 2, or indeed, kinetic energy is 1,000 joules, which is what we suspected because we knew that's how much work we did. So there we can see that that's the correct equation for kinetic energy, and there we can see that if you push on an object and you cause it to accelerate over a certain distance, the work done, which is force times distance, must equal the kinetic energy obtained at the end, assuming that none of the energy is lost due to friction or any sort of resistance, wind resistance, you name it, and none of the work is used to gain potential energy. If all of it is used for kinetic energy, then all of the work is then converted to 1/2 mv squared. That's how you do that.